Hey everybody, welcome back to another video in the series Python for Linguists. Today we'll be talking about conditionals, which are going to enable us to make decisions, to execute code only when certain conditions are met, right? Hence the term conditionals. So very often in linguistic analysis, we don't just want to treat every word equally. We want to do something, but not necessarily to every word. So for example, we want to filter out stop words. We want to only, consider some feature if we're looking at a noun and not a verb, etc., etc. And for this, we need conditionals that sort of tell us, okay, in case we have now encountered a relevant form, we can do something, have Python execute some code. The underlying logic of all of this is Boolean, and that's really just saying a thing can have two states, true or false, right? So Boolean logic just divides the world into true and false statements. So here's a couple of examples which you can try coding yourself in the live shell. Something like 1, and then it's a double equal sign 1. And then the same thing with 1 on the left and 2 on the right of the double equal sign. 2 greater than 1, 2 and then an exclamation point equal sign 1, which are all sort of mathematical and they maybe make most immediate sense, but we can also do really interesting and relevant Boolean stuff with strings and lists. So you can check whether a certain letter is in a certain word, so A in Christmas. You can also check whether 2 letters are in Christmas and see what the results are that you get from that. Then you could sort of check whether a list is in a string, and you can also check whether a list is in a list. And maybe some of these bottom pieces of code will give you cause for surprise. We can quickly implement them here in the live shell. Give me a second. So 1. Okay, Python returns true, right? If we do 2, Python returns false. 1 greater than 2, that's false. But 1 is lesser than 2. That returns true. 2 is unequal 1. We also get a true. A in Christmas. And then TA in Christmas. That's maybe the first one where not everybody maybe was necessarily 100% certain this was going to return false. So we have a T and a T and an A in Christmas, right? But we don't have the sequence, the precise string ta or whatever in Christmas. So this returns false. So it's not checking the individual elements, but whether the whole thing TA is in Christmas. And then you might think, well, a T and then kind of separately an A in Christmas. Sorry for the inconsistent capitalization. That doesn't work at all because a list can't be in a string, right? So not everything goes here. And then if we look at 2 lists, so this looks very similar to, let's say, A in Christmas, or maybe MA in Christmas, which is also going to return true because the precise substring MA is in Christmas. And then we have the basically sublist 1, 2, 3 of the list 1, 2, 3, 4, but we get a false. We'd only get a true if this obtained, right? If this higher level list contained the list 1, 2, 3, then we're going to get true. So it's sometimes important to know what exactly Python is looking for with these conditional statements. But very often when we apply conditionals to strings, it's a pretty straightforward forward procedure. All right, let's get back to the slides here. This really becomes interesting and helpful combined with if statements, right? So now we have a condition, and then with the Boolean that we can evaluate to true or false. And with an if statement, we can actually sort of make the execution of code dependent on whether some Boolean expression is evaluated to true. So a very simplistic and stupid example, we define my integer as 5, and then we just check if, and then here's our condition. We start with the if always, right? And then we just specify the condition, followed by a colon. This is mandatory. So if my int double equals, so is equal to 6, then print this variable equals 6. If you try this, and I'm not going to live code this now, you'll probably just get nothing in return because we don't have something that's equal to 6, right? In addition to the if, we can also specify the inverse of the condition. So essentially that's if we do if and else, the condition in the if that's evaluated to true, we execute the code block here. And note that this is, again, hierarchically organized with indentation, right? If condition, and then sort of there's some code, which can be more than one line, but here it's just one line, that's governed, essentially, that's under the scope of this if statement. It gets an indentation. So if my int equals 6, print this variable equals 6. We don't have that. And then we go back with the else statement. And that's just saying basically if this is evaluated to false, right? And this is on the same level of indentation as the if statement. And then once again, it gets something that's under its scope, so that's indented underneath it. Print this variable sucks. Not very nice. Very often, you can, if you don't want to do something specific with this else, if this else condition, well, if the only thing relevant to do is something if a condition is met, you can simply leave this out, right? So we did this up here. If my integer equals 6, then print something. And that's fully functional code. And very often the else condition is something where nothing needs to happen, and then you can just leave it out. So that's that just makes code a little bit more condensed and kind of gets rid of superfluous keystrokes. And we can even have more than 2 conditions. We can have multiple conditions with an elif statement. So here we're saying if my integer is 6, we print this variable equals 6. If it's greater than 6, we print this variable is huge. And then else, which just means both this and this get evaluated to false, right? We get, and logically that has to be then a number smaller than 6. That's not even 6, is what this code is going to tell us. You can play around with this a little bit. If-elif-else. So if you want to divide your world up into more slices than just kind of a left and a right, for example, you can sort of work with that. And it's quite often the case that we need to work with if, elif, and else. All right. It really gets interesting at the point that we are right now in this class. Once we combine if statements with a for loop, right? In the above example, if I quickly jump back here, I mean, we define one variable that we know what it is, and then it's really pointless to check whether it's 6 because we already know it's not 6, right? That's not interesting. But let's assume that whatever the variable that's checked isn't constant, like isn't something we define and it doesn't change, but is something in a loop, right? Every word in a text, for example, gets a bit more interesting, right? So frequent tasks that we have in corpus analysis and also in NLP is filtering out stop words. So to create a version of our text that doesn't have stop words in it. I mean, stop words mostly are the high frequency, semantically lean or void function words like articles and conjunctions and that sort of stuff that for a lot of tasks, not necessarily for all linguistic tasks, but for a lot of tasks that focus more on semantics, etc., kind of are noise essentially. So they sort of get in the way, and we want to filter them out. And we can do this with a for loop and an if statement, right? So let's assume we have something that's called my text. That's just a list of words. We can define a stop words list. And this is here just a, the, and, but, or, to, of, and in. Note that in reality, this should be a longer list, but this is just a worked example. And then we can define an initially empty word list called my text clean, sorry. We already have my text. And then we iterate over every word in my text. And then if that word is in our stop words list, we simply don't do anything. And if it's not in the stop word list, we actually add it to my text clean. So then my text clean should have simply all of these words removed, right? And that's already quite a powerful thing to do, to like take a text and know something, find out something about its individual elements, and execute commands depending on what we know about these elements. Something to note here are the stacked indentations, right? So forward in my text means basically everything that's happening under here is happening several times, as many words as we have in the text. Anytime we have a new word, we do all of this. And then we have an if statement that's indented from here. And then because that if statement has a command under its scope, that command again gets indented. So this is how Python tells you or represents how you actually tell Python what the logical order of things is. And once you have a little bit of experience with this, Python code becomes really nicely legible because these indents are just something that a human eye can process quite nicely compared to some other ways of sort of representing the hierarchy among different pieces of code. So this is something to get used to, right? There's this potentially infinite number of indents. I mean, you're hardly ever gonna go above 4, I would expect. You usually want to write code that doesn't go above 4, but in principle, it's possible to always add another indent, another piece of code that's sort of under the scope of a previous piece of code. Let's practice a little bit. And here's the task. So on Ilias, in the folder corpora, you'll find the part of speech tagged brown corpus. It's a zip file consisting of, I think, 15 individual text files, and they're labeled brown A through brown R, I think, where the letters indicate different types of written, published English, published in the 1960s. So take one of these files, and then let's just count all the nominal and all the verbal forms ending in the character sequence ing, ending in ing, right? You can do this by defining two variables, ing n and ing v. They're both initialized to a value of 0. So ing underscore n equals 0, ing underscore v equals 0 as well. Or you can abbreviate that a little bit, writing it in one line. I'll leave that up to you to figure out how to do that. Then we'll need the text as a word list, and then we iterate over the word list. And we want to define conditions where anytime we encounter an ing-n form or an ing-v form, we update the counter, these two variables, right? Update their current value by an increment of 1. So that's the task. You can pause the video, sort of work on it a little bit, and you can scroll down here for the solution. Obviously, you can't do that in the video, but I will leave a link to these slides as HTML accessible, both in the video description and at the end of this video. So if you want to sort of check yourself against a model solution, you can do that. Now let's move on. There's a couple of additional things we can do with conditions, and a lot has to do with combining conditions. So we can always latch together more than one condition, 2 or more, with and, just and in between them. So if we want to find all lowercase words longer than 7 characters in a text, let's assume we don't want proper names to be in there, but genuine regular words of the language that are pretty long, longer than 7 words. Bit of an artificial example, but you know. We can do for item in my word list, if item is lower. We'll learn a little bit more about these string operations in just a second. And the length of the item, len item, is greater than 7, print item, else pass. Right, so it's a regular if statement. And so far we've gotten to the point where we'd probably say if item is lower, colon, do something. And that's actually, you know, something we could also do to achieve the same thing, right? We could do if item is lower, colon, and then in a new line, indent it. If this is the case, just specify the next condition. If its length is greater than 7, print item. And then kind of optionally, we can have these else pass conditions, and note they're always aligned here with the corresponding if statement. But you would get away with simply leaving them out if you know everything you want to. The only thing you want to do in the else condition is pass. You don't even actually need to produce that code. All right, and something similar you can do with or. That's really what intuitively, from a sort of human perspective, an or would do, right? If one condition is met or the other condition is met, then do something. So in technical terms, that's if this is met or this is met or both are met. So it's a complete overlap between these two. That's also possible. So we could find all words that start with a lowercase alveolar stop, and we could just go for, you know, element in my word list. I'm changing the loop variable around here just to sort of, as a little reminder that this is an arbitrarily used variable for element in my word list. If element starts with T or element starts with D, print element, else pass. Again, we don't absolutely need the or statement. We could do an if-elif-else sequence, right? If it starts with T, print element. Else, if it starts with D, also print element. And then if neither of these conditions is met, so the else is just the sort of everything that's not captured by the above conditions, pass. You can do the same thing. Here, it's actually, with the above example with and, I think it's very often clear that it makes sense to have it in one line, 2 conditions, because you don't want to additionally indent. Sometimes I think with or statements, you know, these elifs can make the code actually a bit more accessible. So that might be a matter of style. And then finally, we can negate conditions with not, right? So maybe we want to find all words in a text that are not part of a stop word list. Again, we use a different loop variable here. For W in my word list, if not W in stop word list, print W, right? So if it's not, let's assume we defined a stop word list. If it's not in there, print it. the position of the not is where it stops being fully compatible with how a human would do this. Very often you would expect, or very often you're going to make the mistake to say if W not in stop word list, right? Because that's syntactically how we would say it. But the if and the not need to be to be adjacent to each other. So this expression needs to be able to be evaluated on a whole, and W not in stop word list, that's just not a Boolean expression that can be evaluated. So the not needs to attach to the if that makes sense. We've seen a little bit of the starts with stuff. Sorry, there should be spaces here. I'm going to fix that in the document I'll actually upload. So we've seen this starts with method for strings, right? We can test any string for whether it starts with a certain character or character sequence. So that's not limited just to individual characters. So we can, do something like linguistics starts with L. It's going to evaluate to true, right? By the way, lowercase l evaluates to false. There's no immediate way Python knows that lowercase and an uppercase l are the same thing. But we can also sort of check for this. And this also evaluates to true, right? We can define longer substrings, and that's sometimes very useful. And then some other methods are ends with, which corresponds to starts with. So just look at the end, and again we can look for one character, but also, for example, ing if we want all the things ending with ing, right? T in s, this is where the break should be. Whether something is a substring of another string, whether the string T in its precise ordering, right, exists somewhere within S. S dot is lower, is it all lowercase? S dot is upper, is it all uppercase? S dot is title, does it have title casing? So where every new word is the first character of every new word is capitalized. Is alpha, tests whether it's non-empty and all characters are alphabetic. Is digit, tests whether it's non-empty and all characters are numeric. And is alnum, tests whether it's non-empty and all characters are either alphabetic or numeric, so alphanumeric characters. Starts with and ends with, and also T in S. Those are the most commonly used ones. But I mean, checking whether something is uppercase, for example, could be really useful. Checking whether something is a digit, depending on the circumstances, could get you somewhere. So this is not something you probably will remember right away. Starts with and ends with is something you probably want to have at the back of your mind, and all the other ones, you now know where to look them up, and we're good. Let's look at the final exercise. It's kind of a dense little video lecture here, and we'll finish with a longish exercise. So assuming we want to find all words beginning with an alveolar stop, right? That's something we did with the or condition on slide 8. Actually, the code we produced is problematic, right? Because we drew on surface orthographic form, and it's actually going to return a lot of false hits, false positives, because a lot of words start with a T, a letter T, but they don't represent an alveolar stop, but an interdental fricative, like right, think, etc. Or these. So we want to somehow filter out these THs. So write code that deals with this issue. So you go over a word list, and then whenever you find a T or a D, but not a TH, sort of print the item. So it prints all the words in your word list that start with an alveolar stop. Maybe you're doing some phonetic stuff that you're interested in here. It's a bit of a constructed example, but that's the task. Again, when you have access to the slides, you can scroll down here and check the solution. Check whether what you did makes sense against the model solution. And really that brings us to the end of this lecture. What? Not a snake? What's going on? Yeah. Here are my image credits, and you can scan this little QR code to access the slides. You can follow this link, and the link is also going to be in the video description. Thanks for tuning in, and see you soon for the next video.